Let's continue our discussion of the postulates of quantum mechanics. So what postulate have we covered so far? Postulate number one, there's a wave function that has all accessible information about the system. We call that psi, right? And we talked about the Born postulate, which we're going to renumber later, okay? Which tells you what the interpretation of psi squared is. The absolute value of psi squared is a probability density function. So today we're going to talk about operators and properties and just exactly what are those. That has to do with postulate number 2 and number 3. Okay, so postulate number 2 says that for every property of a system, there's a corresponding operator which must be Hermitian. So we have to talk about what an operator is and what is a Hermitian operator. Okay? And postulate number 3 says that if a property of a system is measured, then the only possible outcomes are the eigenvalues of the corresponding operator. So we need to know what an operator is, what is a Hermitian operator, what is an eigenvalue. Okay? And so that's what we're going to have to do first. So let's go over the concepts of operators and Hermitian operators and eigenvalues and all that before we actually tackle postulates 2 and 3. Okay, did I start recording? Okay, let me just make sure. Yeah, I did. Okay. All right. So postulate number 4 also has to do with operators. We'll just skip that for now. Okay, we'll go back to that. Postulate 5 also has to do with operators, the uncertainty principle. So let's just go straight to what an operator is. Okay, so an operator is just something that transforms a mathematical function into another function according to a well-defined rule. Okay, so you define what an operator is. You decide what you want an operator to be. Okay, so let's say, and usually you represent an operator with something that has a hat on it. So this is the letter A with a hat. So A hat, you would read that. Okay, so that's a hat. So A hat operating on function F. So A hat here is called operator A. And you'll see in most of the slides, I don't have that hat because I can't do hats in PowerPoint. So I'm just going to put them in myself as we go along. So A hat operating on function F. What if we define that operator so that we say if A hat operates on a function, it gives you back the derivative of the function. Okay, so in other words, think of an operator as some kind of box. A function goes in, and then a different function comes out. And so this is your operator. Okay, so if f comes in, what comes out is the derivative of f with respect to x in this case. Okay, so this is similar to the way you define a function. You put a number, right? F of x, you put a value of x, you get something else. You get another number. Similar thing, except you put in a function, you get out another function. That's what an operator is. So, according to this definition, then, the rule is if you apply operator A on a function, it gives you back the derivative of that function with respect to x. So, let's apply that operator on x squared. A hat operating on x squared, what would it be? According to the definition, what does it do? It takes the derivative of whatever it's operating on, in this case x squared, with respect to x. So what's the result? 2x. Okay, that's what an operator does. Okay, it is a well-defined rule, and taking a derivative, you have learned very well-defined rules for taking derivatives, right? Okay, let's talk about sum of two operators. Let's say operators A and B. Okay, operate on a function. Okay, what would happen? So that let's just say A operating on F takes the derivative of F. And let's say B, operator B, if you apply that on function F, you get back the square of F. Just for an example, okay? So what would happen if I were to add A plus B, operator A plus operator B, apply that on F? The net result is you just get the sum of A applied on F and B applied on F. So by definition, you say this is going to be equal to A hat F plus B hat F. So that's a definition of a sum of two operators. So that's a definition, okay? You have two operators. The sum of the two operators simply means you apply each one separately and then combine the result. So what's the result if a and b is applied on x squared? So what are we going to do if we have a plus b, we apply that on x squared? Then it's going to be a applied on x squared plus b applied on x squared. What's a applied on x squared according to our definition of a here? It's going to be 2x. What is b applied on x squared according to our definition here? X squared squared, right? So that's just going to give you 2x plus x to the 4th. Pretty simple so far. Okay. Product of operators. Let's say if you have a product of operator A and B. What does that mean? Well, a product of two operators is another operator, okay? And the result of applying a product, okay, on a function, a product of operators on a function is to apply the both operators in sequence, okay, starting with the rightmost operator. So in other words, if I have a product of operator A and B, apply that on a function, what I'll do is start off with the rightmost operator, and that's B. Apply it first. So apply a B on F. So now I'm going to have A, apply that on the result of B operating on F. So I'm going to apply B first on F. That gives me a different function, right? So now I operate A on that function to give me the final result. So product of operators means apply the rightmost operators and then go all the way to the left in sequence. So let's do our simple example again. Let's say operator A takes the derivative of a function with respect to x, and operator B takes the square of the function. Okay? So what would happen if I were to do b hat, a hat, apply that on x squared? What should I do? I have to apply the rightmost operator first, right? So this gives me b hat. What's a operating on x squared? 2x. That's just the derivative of x squared, which is 2x. So now I apply b on the result. What do I get? What do I do to the function when I operate b on it? I square it. So whatever I have in there, 2x, I square it. So the result is 4x to the 4x squared. What if I do a hat, b hat, x squared? Do I get the same result? So apply b first, right? So what's the result if I do that? That's going to be equal to, what is b apply on x squared? That's x to the 4th, okay? So now I'm going to apply a hat on x to the 4th, and that will give me 4x cubed, right? So that means a hat, b hat is not the same as b hat, a hat. In general, we say, okay, operators do not commute. Operator multiplication is not commutative, okay? Operator multiplication is not commutative. But there are some cases where they do commute. And so we say the operators, there are some cases where the operators commute. In that case, that must be for any function. It doesn't mean that if they commute for one particular function, they will commute for every other function. Okay? So if you apply it to any function and they always give you the same result, then that means we say that the operators commute. But in general, When you multiply operators, they do not commute. It matters which order you do it in. That's why we're very precise when we define what it is. You start with the rightmost operator and go to the left, one at a time. Huh? That would be, it's an exception, but it does happen. Okay, so operators do not commute in general. Okay. Let's talk about linear operators. What's a linear operator? A linear operator is one that obeys two conditions. Here's condition 1 and here's condition 2. If I apply operator O on a sum of two functions, f and g, okay, then if it is a linear operator, and that should be equal to applying O on f and then applying O on g and just taking the sum. Now, don't confuse this with A plus B operating on f, which is AF plus AG. That's different. BG. This is different. Okay, this is sum of two operators. This is the definition. This is always true. Okay, this one is always true. Sum of two operators will give you the sum of the results. But this is not always true. And the other condition that must be satisfied is this. If I have an operator operating on a function that is multiplied by a constant, so C here is a constant, I should get back, it should be equal to the same, it should give me the same result if I just took the operator on F, apply the operator on F and multiply it by the constant. In other words, I should be able to just pull that constant out of the operator. And again, this one is not always true. Okay, so if both of these conditions are satisfied, if both of these are true, then you say that the operator is a linear operator. In fact, you can combine this expression. Okay, in some textbooks, this is how a linear operator is going to be defined. Operator O is a linear operator if you operate it on C1 F1 plus C2 F2. Okay, or C1 and C2 are constants, F1 and F2 are functions. If that gives you back, okay, I can distribute, right? Because that would satisfy condition 1, right? So that's O C1 F1 plus O hat C2 F2. That satisfies condition 1. And if it satisfies condition 2, what can I do? I can pull out my constant. So that gives me C1 O hat F1 plus C2 O hat F2. So this is another definition of a linear operator. Okay, this is a more compact way of defining the linear operator. You can either say if the operator, if this is true for the operator, it's a linear operator. Another way of saying it is it's linear if it satisfies these two conditions. Okay? Now, F and G, okay, the F and G that we have here can be any arbitrary functions. It doesn't have to be if it works for one specific pair of functions, it doesn't mean it's true. It has to work for any pair of functions. So F and G must be arbitrary. So let's say we define operator A as follows, same definition we did earlier. A operating on function F gives you back the derivative of function F. Is A a linear operator? Now let's see. A hat operating on function F plus G. Is that equal to A hat operating on F plus A hat operating on G? Well, let's do it step by step. What's A hat operating on F plus G? That's derivative of F plus G with respect to X, right? That's the definition. A hat operating on anything will just give you back the derivative of whatever it's operating on. In this case, it's operating on F plus G, so it has to give you the derivative of F plus G with respect to X. Okay, but what's the derivative of F plus G with respect to X? You know that that's equal to dF dx plus dg dx, right? You know that from math, from calculus. But what is D operating on F? That's just AF, right? That's A hat F. And what is dg dx? That is just A operating on G, right? So plus AG, A hat G. So that's that. So condition 1 is satisfied. Let's look at condition 2. A hat operating on F plus G, constant times F, is that equal to a constant times A hat operating on F? Again, we prove this step by step. Apply the definition first. What's the definition of operator A? Whatever A is operating on, you just take the derivative with respect to x, right? So derivative with respect to x of CF. Now, what do we know about derivative of a constant times a function? I can pull out my constant, right? Times derivative of f with respect to x. But what is df dx? So that's just c times a hat f, which is that. So the answer is yes. So conditions 1 and 2 are satisfied. So the derivative operator, a hat here, which takes the derivative of a function, is a linear operator. It satisfies both conditions. All right. Let's say we define operator B, same as before, takes the square of whatever function it operates on. Is that a linear operator? Let's see. A hat B hat operating on function f plus g. Is that equal to b hat f plus b hat g? No? Okay. Let's see. What does b do to whatever it's operating on? It takes the square. So it takes the square of f plus g. But what's the square of f plus g? F squared plus 2fg plus g squared. Okay, and what do we know about f squared? F squared is just b hat f, right? And g squared is just b hat g. But there's an extra term here, that's 2fg. Oops. There's a 2fg in between, right? So that's equal to that, that's equal to that, but there's that that's extra term here. And the only way this would be true is f and g are both 0, right? Or one of them is 0. So condition 1 is not satisfied, right? So B is not a linear operator. You don't even have to test the second condition. But let's test it anyway. What's the second condition? B hat operating on CF. Is that the same thing as C times B operating on F? What does B do to the function? Squares it. CF squared. And so that's equal to C squared F squared. And what is F squared? That's just B hat operating on function F. And when can this be true? If C is equal to C squared. In general, C is not equal to C squared. The only way this can be true is if C is 1 or negative 1 or 0. Yeah. So in general, then the answer is no, right? So B is not a linear operator as we have defined it here. Okay? So you know what a linear operator is. Is C operating on function f gives you the complex conjugate of function f. Is that a linear operator? Okay, I'm going to give you the answer, and you have to prove it to me in the homework. So I'll add that to your homework. The answer is no. All right. Let's look at some types of operators you might encounter. A lot of operators you might encounter would be involved something that involves replacement. So replacement type operators, these are generally linear. Okay, so consider the parity operator, f of x. So pi hat here, the parity operator, operates on a function of x. And the rule here, when the way this is written says that anytime you see an x, replace it by negative x. Okay? So let's just assume x is real. Okay? So it's a parity operator because x is coordinate. Okay. So it's a parity operator, a linear operator. Let's try it. Parity operator operating on f of x plus g of x. Is that the same as parity operator operating on f of x plus parity operator operating on g of x? Now, let's see, what's the left side equal to? Anytime I see an x, I replace it by negative x. So this is f of negative x plus g of negative x. But what is this? This is just pi hat f of x, right? And what is this one? Pi hat g of x, which is the same as that one, so the answer is yes. Okay? What about a constant? Parity operator operating on a constant times f. Is that equal to a constant times parity operator operating on f of x? What would you do here? Anytime I see an x, I replace by, so this is c times f of negative x. But what is f of negative x? That's c times parity operator operating on f of x. And that's the same. So the answer is yes. So the parity operator is a linear operator. Okay. Another type of operator you'll encounter is what's called a multiplicative operator. Is it time? Okay, we'll continue this next time.